In this video, we will talk about the side-side angle ambiguous case of the law of sines. We'll be doing a worked out example. See the first video for a more conceptual framework. So for this problem, we're given a triangle ABC with angle A being 37 degrees, side little a being 12, side B being 17. So first of all, let's draw ourselves a picture. Here's mine from GeoGebra. Obviously, if I was going to be doing this on paper, I would be drawing this by hand. Secondly, let's go ahead and calculate the height. This will help us determine how many triangles end up being possible. Angle A, which is 37 degrees, is made up of two rays, one of which is side C and one of which is an unknown length. The height is the distance point B is away from the unknown ray. So I'm going to use my sine function since the height is opposite of angle 37. So sine of 37 equals the opposite over hypotenuse, so height over 17. And let's go ahead and multiply both sides by 17 in order to solve for the height. So I get that the height is equal to 17 times the sine of 37 degrees. Let's go ahead and get our calculator out so that way we can find the decimal approximation for this value. So the height is approximately, here we go, 17 times sine of 37. Now make sure that you are in degree mode. And that gives us 10.23. So the height is about 10.23. Now if you notice here, side A is 12. And so that is longer than the height value, but it's not quite as long as the other given side length, which is side C, which is equal to 17. And from the previous video, you will have learned and you have found out that if the height value, if your side opposite the known angle is between the height value and the other side that you're given, so in other words, in this case, side A is in between the height and side C, which it is, we're going to have two triangles possible. And we'll do a quick visualization of that with GeoGebra once again. So as you see here, as you move point C around a distance of 12 away from point B, there are two separate locations where it will hit the ray that makes up angle A, giving us this purple-blue triangle and that original orange triangle that you saw at first. So there are indeed two triangles that will be possible. So we will be solving for both sets of values. So we're going to be solving for the missing sides and angles in both ABC1 and ABC2. And as you can see here, notice both of those values, B to C2 and B to C1, those values are exactly the same since we created it by using the radius of a circle. So we're going to go ahead and find the missing values for that first triangle that we saw, the orange one. So I'm going to set up my law of sines. Sine of 37, which is the amount of angle A, over its opposite side, which is 12, is equal to the sine of C1, our missing angle amount, over its opposite side, which is 17. Now I'm going to go ahead and I am going to multiply both sides by 17, and I get sine of C is equal to 17 sine of 37 over 12. And then to solve for my angle, I'm going to use my inverse trig function, my inverse sine. So I take the inverse sine of that ratio, and it's going to tell me what angle amount produced that value. So let's go ahead and get our calculator out, and I'm going to do sine inverse, and I'm just going to type this all in at the same time. 17 sine 37 divided by, see that's the numerator, so I want to make sure I closed that parenthesis, divided by 12. And now I'm going to close the parenthesis for the sine inverse function and hit enter. And it tells me that angle C1 is 58.49 degrees. And I'm going to store this value into alpha and then C, so that I can use this value later and I don't have to round it, and so that way I'm able to have a very accurate set of results. So angle C is 58.49 degrees, which seems reasonable based on my sketch. So I've got 37 degrees there, 58.49 degrees there, and since we're living in the land of triangle, the sum of the three angles of that triangle should be equal to 180 degrees. So angle B in this triangle is going to be equal to 180 minus angle A and minus angle C, 1. And I'm going to call this angle B1 just so that I can stay consistent with the fact that this angle represented angle B from the first triangle. So let's go ahead and calculate that. 180 minus 37 minus alpha C. Therefore, I haven't done any rounding, and so I'm not going to round a rounded answer. So it gives me 84. So angle B1 is equal to 84.51 degrees. And now, last but not least, for triangle 1, I'm going to solve for side little b, the side opposite angle B. So once again, I'm going to use the law of sines. So sine of 37 over 12. I'm going back once again with the fraction value of values that they gave me as opposed to something I calculated, just in case I made an error. And that's equal to sine of 84.51 over b. Oh, I want to make sure also that I stored my b value. So I store angle B into second B there before I go ahead and use this to make a calculation with. So I'm going to cross multiply. So B sine 37 equals 12 sine of 84.51. So side little b, to get that by itself, I'm going to divide both sides by sine of 37. And let's get our calculator out. And luckily I have that 84-degree angle stored. So side B1 is equal to, and let's move the calculator over, and I'm going to do 12 sine of B, since I have stored that value. So I just have to do alpha and B there, divided by sine of 37. Enter. Therefore, the length of side B is about 19.85. So these are the three missing components for the first of the two triangles that were possible in this scenario. Here are those values put into the picture. Are we done yet? Nope, we're not finished. We still need to find the missing sides and angles for the second triangle.
No way!
So as I showed you before, now we're talking about ABC2, the purple triangle, and as you notice, side B to C1 is the same length as B to C2. They are both a side length of 12. And therefore, because of our isosceles triangle theorem, if two sides of a triangle are congruent, then the angles opposite them must be congruent as well. So let's go ahead. I'm going to put that 37 degrees back in there. And we already calculated angle C1. So I'll put that into my diagram. So that was 58.49. And therefore, angle BC2 to C1 is also 58.49. And so the angle C that we care about, which is angle C2 in the purple triangle, in other words, angle AC2B, that is going to just be the supplement of angle C1 that we already calculated. So I'm going to do 180 minus, and I already have that value stored in C. So hit enter, and that gives me 121.5. And since I'm going to be basing my calculations on this new value of angle C, I'm going to store that into variable C. So I'll go ahead and store that into C. All right. And it should make sense from our diagram. It seems reasonable that that should be an obtuse angle in this case. And now, if we know that we have in the purple triangle an angle of 37 degrees, an angle of 121.51 degrees, and the sum of the three angles of a triangle is equal to 180, then that third remaining angle, A to B to C2, in other words, our angle B sub 2, should be 180 minus angle A minus angle C2. So let's go ahead and grab my calculator, and I have this new value of C stored in there. So I'm going to do 180 minus 37 minus angle C, which is the 121. And you always want to pause and ask yourself, does my answer actually make sense for my rather reasonable picture that's drawn? Don't just rely on whatever number the calculator spits out. Pause and kind of think about it for a second. All right, so that last remaining angle is 21.49. And now let's go ahead, and I'm going to store that into B now, since we're going to use that angle amount. And we're going to set up our law of sines once again. Sine of 37 over 12 equals sine of 21.49, which was our angle B, over side little b. Let's go ahead and cross multiply. So B sine of 37 is equal to 12 sine of 21.49. So B is equal to 12 sine of 21.49 divided by sine of 37. Which is approximately 12 sine, and since I've stored the new B value, so 12 sine of angle B divided by sine of 37 gives us 7.31. And it seems reasonable that this side length should indeed be smaller than the first option for side B that we calculated. So those are our three values for that triangle. And that's the 7.31. So, just to organize our work a little bit more, I've listed out for triangle 1 the sides and angles that correlate to that solution, and for triangle